Welcome to day 5. Today we're going to review polar coordinates and polar functions from what you did in pre-calc honors. So first our homework. So we wanted the arc length. So do your dx dt, your dy dt, square them each atom under the square root. And this is the one that you could do in your calculator. So you got 5.916. In 36, again, we want arc length. So do your dx dt, dy dt, put them in your square roots where they're squared, and add it together. So we wanted you to try this algebraically. So when you square them both, you then have a 4t squared that you can pull out, which would be under a root. Well, the square root of 4t squared is the absolute value of 2t. Because we're going to be going from -1 to 0, we would want that to be a minus 2t. We could then do our u substitution. So u equals 1 plus 36t squared, so your du is 72t. Multiply both sides by 136 and then just keep the negative out front. So now you have u to the 1/2. You can switch your bounds from -1 to 0 and it becomes 37 to 1. You just keep them in the same order based on what you got. So now we will fill in after we do our antiderivative. And your exact form would be on the left there, -1/54 times 1 minus 37 to the 3/2, and to 3 decimal places, if you then punch that in, would be 4.149. 37, another arc length. So do your dx over dt, which you had to do a product rule. Do your dy over dt, which you had to do a product rule. We'll square those and add them together, put it under a radical. Well, when you square them, when you multiply it out, we end up getting this step here. We get two terms that will wipe out, because one's positive, one's negative. And then we had some like terms to combine. So we end up having a coefficient of 2 in front of each of those terms. Well, see what you can pull out of each term. You can pull out a 2e to the -2t. The square root of that would be square root of 2 times e to the -t. And then the cos squared plus sine squared is just 1. Your antiderivative of e to the -t is minus e to the -t, so we get the negative radical 2e to the -t. Fill in your pi over 2 and 0, and you got your exact form, and then you got rounded to 3 places. So the next one, our graph of this, notice has corner points, so we have to do the 4 times just 0 to pi over 2, like we saw in the lesson. So take your dx over d theta, dy over d theta. When we square them, there's no addition or subtraction, so we just square each of the terms. A is a constant here, so you can pull out 9a squared, cos squared, sine squared, all under a radical. So the cos squared plus sine squared under the radical, that's just 1. Take your square root of the other part, we get 3a cos sine. You can let u equal either of them, but sine might be easier because then you don't have to correct. U is sine, du is cos. So you just have u, change your bounds, do your antiderivative and fill in, and you just get 6a. 49, we're now doing surface area. So your dx over dt was 1, your dy over dt was 2. The only difference in part A and part B, part A you're going over the x-axis, so your y part should be for the radius, and in B, the x part should be the radius because you're going over the y-axis. So that neatens up pretty nice because you get a square root of 5. You can just pull that out front with 2 pi and the other constants. So you're just doing the antiderivative of t in both cases. And notice your answers just differ by a factor of 2 because you had 2t for the one radius and t for the other. We got another surface area, so do your arc length with your dx over dt, dy over dt, square them, add them together under the radical. This one was going over the y-axis, that's why our x is the radius. You can pull the 4 out. When you square the things under the radical, you can take out a square root of 16, which would leave you with the sine squared plus cos squared, which is just 1. So then I took that square root of 16, or in other words 4, just put it out with the 8 pi to make 32 pi. Do your antiderivative, sub in, you get 32 pi. In 52, we were again going over the y-axis, so your x part was your radius. When you neaten up under the radical, this ends up as a u substitution. You got to correct by a fourth, change your bounds, do your antiderivative, and fill in. So you got your exact form there, the pi over 9 times 17 to the 3 halves minus 2 to the 3 halves, and to 3 decimal places. All right, so we'll be on day 5 in our notes packets. And we're going to look at polar coordinates and polar functions. So a polar coordinate is in the form r comma theta. So any point could be written in rectangular form, so that would be the x comma y, or in polar form r comma theta. The r comma theta tells us how far from the pole, which is 0, 0, and what angle from the polar axis, which is that x-axis on the right. So if we wanted 2 comma 3 pi over 4, if we wanted to plot that, well, 3 pi over 4 is the same as 135 degrees. And basically it means, imagine you had a circle of radius 2. We would want to go 135 degrees on that circle of radius 2, and that would give us our point for that polar coordinate. So that dot right there would be 2 comma 3 pi over 4. Now, if you have a negative radius, it sends it to the opposite ray. So pi over 2 would be right here. But because we go negative 5, it's negative, so we go in the opposite direction. So we actually end up going down. So because of that, there's always 2 ways you can write polar coordinates. So we could have done negative 5 pi over 2, or that's the same location as positive 5 3 pi over 2. Both of those will get us to the same spot. The negative is when you send it through to the other side. So we're going to take that smiley face point there, and we're going to see if we can write it in a whole bunch of different ways. Well, first off, we know our radius is 4. So let's imagine we went around like this to get there. Well, that's pi over 6 short of 2 pi. 2 pi is the same as saying 12 pi over 6. So that would be 11 pi over 6, and we would have a radius of 4. Well, you also could have went backwards to get there. So we could have had a radius of 4 and had negative pi over 6. Well, another thing we could have done is we could have gone to the second quadrant and then done a negative radius. So we would want the pi over 6 reference angle there again. So that would mean that green kind of circular arc would be 5 pi over 6. So we could do a negative 4 radius and an angle of 5 pi over 6, and that would send it to the smiley face. Now, a similar idea is you could have gone backwards to get here. So that's pi over 6 beyond pi. So that would be going negative 7 pi over 6 for our angle, and our radius would be negative 4 because we would send it back. Now there's really an infinite number of possible polar coordinates because each of these you could do plus or minus 2 pi to your angle. So converting to polar coordinates. So some things we know based on this triangle setup is that sine of theta is the same as y over r. So if we multiply the r over, y is just r sine theta. And likewise, cos is the adjacent over the hypotenuse, so cos theta would be x over r. If we multiply the r over, we have x equals r cos theta. So that's one thing that involves x's and y's. Some other ones we know, if we do Pythagorean theorem, we'd have x squared plus y squared equals r squared. So that's another one that we have. And then the last one, if we want to represent theta, theta is equal to either tan inverse or arctan of y over x. Because you've got the opposite over the adjacent. If you do the inverse tan, that should give us the angle of theta. So if we want to convert this into rectangular form, so that's our xy form, we have that x is equal to r cos theta. So x is equal to our r of 4 times cos of 2 pi over 3. Well, 2 pi over 3 is 120 degrees. So that's a 60-degree reference angle in the second quadrant. We would have square root of 3, hypotenuse would be 2, and the adjacent side would be negative 1. So therefore, our x is just going to be 4 times our adjacent over hypotenuse of that reference triangle. So that would be negative a half. So our x is just negative 2. Similar idea for y. Y is equal to r sine theta. So we'll have y equals 4 sine of 2 pi over 3. So y is equal to 4 times the opposite over the hypotenuse. So that's times square root of 3 over 2. So y is just going to equal 2 radical 3. So in the end, our rectangular coordinate is negative 2 comma 2 radical 3. Now a little spot check that you can do to see if your answer is reasonable is 4 comma 2 pi over 3. Okay, if you go 120 degrees and go out a positive radius of 4, that's in the second quadrant. See if your rectangular point is also in the second quadrant. Well, we go 2 left, we go up 2 square root of 3, that is also in the second quadrant. So just checking to make sure they're both in the same quadrant can help catch any little errors. All right, moving down to the bottom, we're going to do 2 going from polar to rectangular, and then 2 going the reverse. So we'll do the 2 polar to rectangular ones first. So we'll do the 6 pi over 2. So our x is going to equal r times cos of our angle. Cos of pi over 2 is just 0, so x is going to be 0. So we've got 0 comma something. Our y will equal our r sine of theta. Sine of pi over 2 is just 1, so we'll get that our y is 6. So 0 comma 6 would be our rectangular coordinate for that first one. Let's jump down, we'll do the bottom one, same idea. X is equal to our r, 8 square root of 3, cos of 4 pi over 3. Well, 4 pi over 3, that's the same as 240 degrees. So that's a 60-degree reference angle in the third quadrant. We'll have minus radical 3, minus 1 for the adjacent, and 2. So this is really x is equal to 8 radical 3 times our cosine, which is negative 1/2. So x is really minus 4 radical 3. Similar idea for the sine. We'll have y equals 8 square root of 3 times sine of 4 pi over 3. Going from our reference triangle, the sine is negative radical 3 over 2. So the 8 divided by 2 is 4. Radical 3 times negative radical 3 is negative 3. And 4 times negative 3 is negative 12. So we get negative 12 for the other part. And notice that point is in the third quadrant, so that's consistent. All right, so for the other two, go in the other direction. We'll start out, we'll find our R value. because we should have r comma theta. And what we'll do is we'll do our x squared plus y squared equals r squared. So we're going to have negative 2 squared plus 2 squared equals r squared. So that's going to be 8 equals r squared. So r will equal plus or minus 2 square root of 2. Well, now let's think about our theta. So theta is going to equal tan inverse of the y over the x, so 2 over negative 2. So that means that theta is equal to tan inverse of negative 1. Well, we get a 1 from a 45-degree angle, so a pi over 4. And if it's negative, we could have that come from the fourth quadrant or the second quadrant. So our options for our angle is we could have theta is equal to negative pi over 4, because that would be a 45 reference angle in the fourth quadrant, or you could do theta equals 3 pi over 4 if you're in the third quadrant. That would be 45 in, or sorry, second quadrant, 45 in the second quadrant. Now to write our point, we just got to be careful. Negative 2 comma 2 should be in the second quadrant. So let's say that we were going to use the 3 pi over 4. We've got to think about which radius we would want to use. Well, 3 pi over 4 is in the second quadrant. We would want to keep it there, so we would use the positive radius. If we use the negative pi over 4, that's in the fourth quadrant, we would then want the negative radius to send it through to the second quadrant, so that would mean our radius would be negative 2 radical 2. So we've got two options for that one. So let's see if we can do a similar idea for the other one. We'll have 3 radical 3 squared plus 3 squared equals r squared. That's 27 plus 9 equals r squared. Or r squared equals 36. So r will equal plus and minus 6. Theta is going to equal tan inverse of our y over our x. So that's 3 over 3 radical 3. So that's theta equals tan inverse of 1 over radical 3. And if your opposite is a 1 and your adjacent is a radical 3, then we should be thinking 30-degree reference angle. If tan is positive, then we should be in the first or the third quadrants. So that means we could have pi over 6, or a pi over 6 reference angle in the third quadrant would be 7 pi over 6. Now just think about what quadrant we're in. We want our point to be in the first quadrant because x and y are both positive. So if your angle is going to be pi over 6, that's in the quadrant that we want, so we would want to use the positive radius. If you decide to use the 7 pi over 6, well, that's in the third quadrant. We want to send it through to the first quadrant, so then we would want to use the minus 6 for our radius. So if it asked for a coordinate, a polar coordinate that represented one of those middle two, either of the answers is correct. It's an or. Now, the reason you have to be comfortable with both is if it's a multiple choice, it might only have one or the other as the choice. So that's why you want to be comfortable writing it both ways. All right, so we're going to graph a polar function. So we're going to graph 3 sine 2 theta. And we're going to go to a graphs page. We've got to go to menu, graph entry edit, and we've got to switch it to polar coordinates. Make sure you're in radian mode. And we've got 3 sine of 2. And we've got to put in theta. Theta's down with the pi. And go ahead and hit enter, and we get our graph. Next, what I want you to do is we're going to do a trace. So do menu, trace, graph trace. And we can just hit our right arrow, and notice it's going by 0.1 radians at the time. I want to go back to where the start was. So it's starting here. So notice it does the loop in quadrant 1 first, but then notice it goes to the loop in quadrant 4 next. And then after this, it goes loop to quadrant 3. And then we do the loop in quadrant 2. Now notice as we're completing our full cycle, we're around 6.2 radians. We're not quite done yet. I'd have to go to another one. But 6.2 radians, that's roughly 2 pi. So it's taking 2 pi for this to go around. It won't always take 2 pi. That's why it's helpful to do this graph trace to see what your interval is. So this curve is actually complete for theta is greater than or equal to 0 or less than 2 pi. And we didn't want to say the equal to because then you're actually on the graph again. So just to kind of show how this looks, so we had our loop here, then we had our loop there, then our loop there, and our loop there. And those are all congruent, those loops. My picture is just not quite perfect. On the bottom, you just have a list of your conversions again. So tan theta would be y over x, and this would be r squared. But we have each of those things from before. We just have it written as tan theta is y over x instead of theta equals inverse tan y over x. And our last page for today, if you go to the next one, we're going to do a couple conversions. So we're going to convert these to rectangular form. So if you have x squared plus y squared equals 16, we know x squared plus y squared equals r squared. So we would say r squared equals 16. And when you have your equation in polar form, you really usually want r by itself. So if we take the square root, we could say r is equal to plus or minus 4. Well, that rectangular form top one is a circle centered at 0, 0, radius of 4. This polar form is doing the same thing. If you do the positive 4, it's just plotting out a radius of 4 in the quadrant that you're actually currently looking at. Whereas if you do negative 4, it'll just plot on the opposite ray first. So positive 4 would start and do quadrant 1, then do quadrant 2, then 3, then 4. If you do negative 4, it would start with quadrant 3, then plot quadrant 4, then 1, then 2. That's the only difference, is the order that it's being plotted in. All right, the next one, we know x is equal to r cos theta plus 2 times y is equal to r sine theta, and that equals 5. Well, we usually want to get r by itself, so we'll pull an r out, and we're left with cos theta plus 2 sine theta equals 5. Well, we'll just divide that over, and that'll have r by itself for us. So r is equal to 5 over cos theta plus 2 sine theta. And moving down to the bottom, we're going to go the reverse direction now. We're going to start in polar, and we want to do rectangular form. Well, sine theta, we know that y is equal to r sine theta. So we could get sine theta by itself and say y over r is equal to sine theta. So that's our first substitution we'll do. R is equal to y over r. Well, if you then multiply the r over, you've got r squared is equal to y. And then we can replace the r squared with what we know it is equal to. So x squared plus y squared. So our equation is just x squared plus y squared equals y. So secant can be written as 1 over cos theta. Well, if we multiply the cos theta over, that's r cos theta is equal to 1. R cos theta is the same as saying x. So x equals 1 would be our rectangular form. So that's a vertical line at x equals 1. So it's kind of interesting to think that our polar r equals secant theta is actually would just show up as a vertical line. So we have that theta is equal to tan inverse of y over x. So we would then write tan inverse of y over x equals pi over 4. So that means y over x equals tan of pi over 4. Tan of pi over 4, that's tan of 45. Your opposite and adjacent are each 1. So we would get y over x is equal to 1. So you could write it like that or multiply the x over and you get y equals x. And if you think about visually, that makes sense. If you had a pi over 4 angle, there's all your positive radii, there's all your negative radii. That's the same as y equals x. All right, that's it for today's video. Have a great rest of your day.